the continue on our notes is 1, 2, 3, and this is the fourth one. So this one is about the rotation of the coordinates. So rotation is one special application of the transformation. Transformation could be, yeah, okay, we talk about this one. So for example, if we look at here and say if we are given a coordinate system, this is I and J and K, and right now I place the I into here because I have some purpose. Okay. So right now for this case, say example, say I want to rotate this coordinate system about I-axis in this angle, in this orientation by theta, and we want to know what is the rotation matrix for this case. Okay, so for this one, basically here, let me, because the rotation will be on the JK plane, so let me lay out the JK plane. Okay, so basically this is a JK plane. Okay, so after the rotations, then say J rotate to J prime, and this is theta, and K rotate to here, that is K prime, and this is theta. Then we see. So again, this one we simply project the components. So this one is the two components. Okay, so for example, this component is cosine theta, and this one is sine theta. So in a similar way, so here we can write it out is this. In our old coordinate x, y, z, and if we want to find out the corresponding coordinates, the coordinates in the new systems, okay, the same thing we simply need to find out is the contents of x prime. So right now this is the x, y, z corresponding is I, j, k. So in terms of x prime, this is our I prime directions. So basically I equal to I prime. So here that is 1, 0, 0. Okay? And then for here j prime, so j prime we simply decompose into jk. So from here you can see this is the magnitude cosine theta in j directions. So cosine theta. And this is the sine theta in k directions, sine theta. Okay, and there's a no projection in the x direction, so that is 0. Okay, and the same thing here for this. Okay, the same thing, this amount is cosine theta, and this amount is the sine theta. So we follow up this one. So this is cosine theta in k direction, so cosine theta. And this amount is sine theta in the negative j direction, so negative sine. And this is 0. So here, this is the rotation matrix or transformation matrix for such a case. So for example, we can do one more and see. So again, this is I, J, and K. So right now, say if we want to rotate J by an angle theta, okay, we see how can we come up with this transformation matrix. So again, let me highlight this is the IK plane. Okay, and here what we can rotate is in this. So here is the new coordinate system. So here, this is theta, and this is theta. So this is our K prime, and this is our I prime. Okay. So the same thing, we simply project. So this is cosine theta, this is sine theta. The same thing, cosine theta, sine theta. Okay, with those things labeled, we can write it out. So for the coordinates x, y, z in the old coordinate systems, and x prime, y prime, z prime in the new. Okay, so now we look at here. For I prime, that's a new I-axis, and that expressed in terms of the old one. So this amount is cosine theta in which direction? In I direction. So that is cosine theta. And this amount is the sine theta in negative k direction. So that is minus sine. Okay, and there's no projection in the y direction, 0. And for y, and this is y-axis, and that is the same, so 0 equal to 0, 1, 0, because j equal to j prime axis, so that's the one here. Okay, and then for z prime, so again, this is the cosine theta, and this is sine theta, 0. Okay? We good? Okay, so probably you can do the exercise. The last one is about the rotating about the k-axis, and I leave that to you. Okay, that should have a similar patterns here. The fifth one is if we want to rotate the system a couple times. So here is so here is this in concept. If this is the first corner systems, and we do certain transformation or rotation, we get to the second corner system. They are all still in Cartesian corner system, and then we do another transformation. We get into the third corner systems. Okay, and then we want to find out the relation of the coordinates between 3 and 1. Okay, so here we can try. So say, let me use the x, y, z as the first coordinate system, and x prime, y prime, z prime, sorry, as the second, as the coordinates corresponding to 2, and x prime, double prime, y double prime, and z double prime for coordinates for the third systems. Okay. So from our equation, we know is this x, y, z. That is the old one. And say here, before we move in that one, we need to know the configurations. So say here, if we are given, we know the relative configurations between each. So that means here, implying we know the transformation matrix R1. Okay, so R1 is the transformation matrix between here to here. And also the same thing, we know the R2. So which means we are given the relative configuration, so we can always figure out the R, the transformation, just like we did here. Okay, so here I would say the given those things. So under these situations, say here, this is our new coordinate system to x prime, y prime, z prime. So the relation is R, right? So that is our tables we've been talking about. So that means the x, y, x prime, y prime, z prime equal to R1 times x, y, z. Okay, similar way here. we have the new old coordinate systems, x, y, z. So that means right now I'm talking is from 2 to 3. Okay, and so here the everything respective to you is old one and the new one. So that is the R2. So that means in terms of the calculations, x, y, z prime equal to R2 times x prime, y prime, z prime. Okay, and then we can plug in the relation x, y prime, z prime, and because x, y, z prime have that relation, so that is R1 okay, so simply I replace this one by this relation, so R1 times x, y, z. So therefore from here you can see x prime, y prime, z prime equal to R2, R1 times x, y, z. So which means if you want to have a successive, say, directly from here to here, basically the rotation matrix is, for this calculation, is R2, R1. Okay, so basically that is the information here. I don't want to write here to confuse, but that is the rule. So if you want to do twice of the transformations, rotations, basically the rule is this. And R1, R2, that is corresponding rotation matrix. So on the other side, if you want to reverse, so say I want to know x, y, z, in terms of how much in terms of the new coordinate systems. Okay, so simply this one, you simply is get the inverse. So for this case, simply in terms of calculation, this term, I'm going to write it and erase it. So you simply look at this carefully. So if from here, if you know in terms of the matrix, if we have, say, y equal to a times x, then we can write it up x simply equal to a inverse times y, right? So we use these properties. Okay, so I use this property. So simply that is R2, R1 inverse. Again, inverse is very bothersome, very rigorous calculation. So basically this one, this term equal to R2, R1 transpose. Okay, I utilize the properties we just described, and this one basically is R1 transpose, R2 transpose. So let me rewrite here. So that means xy z equal to this multiplied with x prime, y prime, z prime. Okay. Any questions? And later we will reuse those properties in our number crunching kind of exercise.